All right, welcome guys to MAE 242 Recitation 1. This is the first recitation for the fall 2025 semester, so congrats, you made it to another semester. And again, I'll be posting all of these, or most of them at least. I have to do them for the online section. But for those of you in person as well, yeah, I should post all of these. Expect them Monday evenings, something like that. Just depends on whenever I get a chance to do them. Right now I'm at my desk in my apartment. Hopefully I'll try and record them during one of the in-person sessions, so they should be up a little quicker. But anyway, so let's get started with this first one. So as you can see, we have a taper plate with varying pressure and table support. So we have a thin horizontal plate. It extends from x equals 0 to x equals L. So width varies as W of x equals W naught times 1 minus x over L from 0 to L. So linearly tapers to tip at x equals L. And I drew it poorly, but whatever, you get the idea. It's supposed to be a tip. It's just a triangle, whatever. And it has a uniform thickness, okay? So we're not going to be doing anything with like the thickness element of it, right? So everything is going to be in terms of like kilograms per square meter and newtons per square meter instead of the full volume of it. If you wanted to convert everything to volume, you just, for the density and whatever. It's not a big deal. It's fine. Blah, blah. It has mass density rho A in kilograms per square meter, like I said. A gravity G acts downward. A downward pressure distribution acts on the top surface, uniform across the width at each x, but varying along the length, as P of x equals P naught times x over L all squared, newtons per square meter. So that P of L equals P0. So at the full length, it's just P0, P naught. The plate is supported by a pin at end A and a cable at B with tension T upwards. So there'll be a tension force coming up here. But we'll get to that later. So for part A, one says to replace P of x with a single resultant force, Fp, and locate its line of action, Xp, measured from A. For B, you want to compute the total weight, W, of the plate and location of its line of action, Xw. And lastly, C, use the resultants from above to determine the tension and vertical reaction at the pin RA. So pretty easy, not too bad. So let's get going with this one. So for part A, like we were saying, we want the resultant of the pressure, P of x, its magnitude and its location, essentially. So what we want to do first is we want to, obviously, since we're dealing with, like a tapering object and things like that, and a varying width and varying force, things like that, we're going to be dealing with differential elements, right? So first off, let's try and formulate what the differential area element will look like, right? So we call that dA, right? Imagining some thin little strip dA. And this is equal to the width at any x location multiplied by that differential dx element that we're stepping by. So it'll literally just be W of x dx, right? And what do we already know what Wx is. We have it right here. So this will be dA equals W0, W naught, 1 minus x over L dx. Cool. So we have that worked out. And now for the force term, we just multiply this dA times that varying pressure that we already have. So we'll also just call that dF is equal to P of x times dA. And what do we have? Well, we already know dA, and so let's plug everything in. So in this case, dF equals P naught x over L squared times W naught 1 minus x over L dx. And now all we do, we just have to integrate from x equals 0 to x equals L on both sides. So if we do that, this dF just becomes F, right? We're integrating, so it's fine. So literally FR, our resultant force, is equal to integral from x equals 0 to x equals L of this P0, that's over L squared, W0, 1 minus x over L and dx. And obviously I keep interchangeably using p0 and p naught and w0 and w naught. It's the same thing, whatever. You know what I'm talking about. It's not a big deal. So compute this integral. First off, though, we can, a couple of these are constants. This p and w, those are constants. It's like some value, whatever it ends up being, whatever they want to pre-describe it as. So those can be pulled out. So let's do that. And 0 to L of, we'll have this. Right, now it's a fairly simple integral. Just, distribute the stuff out and then integrate it. This is in calculus class. I'm not going to carry all that stuff out. You got stuff online. Just go plug this in. If you're really in a jam and forget how to do this, it's not that big of a deal. But anyway, you end up getting, it would be like, after you distribute it out, it'll be, something like this. Where it's, right, dx, whatever, and then just go plug it in, solve from 0 to L. So we end up getting FR equals, it'll be like, we'll work out something like that, and then 1/3 minus 1/4, right, from power rule, right? That's where the 3 and the 4 come from. Then simplify all that out, and you get FR equals P0 W0 L over 12. And this will be like, newtons per square meter or whatever, right? Or something like that. Or, should just be newtons. Yeah, it should just be newtons, whatever. Whatever, who cares? Whatever the units are. It's weird because we don't have that third term because we're not dealing with the thickness, so whatever. But anyway, yeah, that's what it is. Whatever the units end up working out to being, whatever. You'll do more dimensional analysis in like a week or two, so don't worry about it. Next, for line of action, we're calling it XP, all right? Line of action XP. We can take this relation. This is like a statics relation, right? Where the line of action XP times the actual force is equal to the integral from 0 to L of x df. And again, we already know, we just did what df is, so just slap another x term on there and you're golden. And then, divide by fr at the very end. So we'll have xp fr equals 0 to L of x times what's df? It's this whole thing up here. P0. All times df. So literally same thing as we did above, but just an extra x term slapped on there. So, drag out the P0 and the W0, distribute the x's, whatever. So you end up getting XP FR. After you do the integral, I'm not going to do the full integral. Who cares? It's fine. You guys can figure it out. We end up getting P0 W0 L squared over 20. Okay, now divide by the FR. So we have XP equals P0 W0 L squared over 20 times 1 over FR, right? So it'll be 12 over P0 W0 L. And so you get the line of action, XP, is equal to just 3/5 L, which is a nice little relation. And this is from point A. Right, all right, so there's part A all done. Yeah, this is from that left end point A, which is right there, right? So it'll be somewhere, 3/5, like right there. Cool. Now, part B. What's part B saying? We want the weight, the full weight of the thing and its line of action, its location, right? And compute total weight of W of the plate and the location of its line of action, XW. Okay, so this one's actually way easier, right? So again, let's do our weight term, right? Literally, what's our differential weight, dW? Well, it's going to be our density times gravity times the area, right? Times dA. So just do the whole thing. We already know dW, or we already know dA. So dW equals rho A times G times W of X dx. And so again, integrate from 0 to L. So we get bid W equals 0 to L rho A G. What's W of X? It's that W0, 1 minus X over L dx. And again, you can pull out the rho, the G, and the W naught and just deal with the 1 minus X over L dx. You can do that, whatever, it's fine. Do the integral. This one's really easy. So we have our full weight, W, after you do all the math for it, is just rho A, G, W naught, L over 2. All of that over 2. Nice, easy relation. And now for the line of action of it, this is literally just like the centroid, I guess. And if you're particularly sharp, right, you can just look at this damn thing and be like, it's a triangle. We drew it bad, and like the PDF document will look the same, so whatever. But it's just a triangle. Where's the centroid of a triangle? Well, it's 1/3 from the thick end. Where's the thick end? It's point A. So it's just gonna be L over 3 from the jump. But if you want to prove it like mathematically, you can use the centroid formula, right? Where XW is the integral from 0 to L of x W of x dx, right? X dA over the integral from 0 to L of dA. And so again, you can go and math all that stuff out and really show it explicitly, but you don't need to. It's just going to be L over 3. But yeah, if you want to prove it to yourself, be my guest. It'll just take you like 5 minutes, whatever. So, we get XW, the line of action, is equal to L over 3 from A again. Right, okay. So now that brings us to the last part C, where we want to use the resultants, use these resultants to determine the tension T and the vertical reaction at the pin RA. So let's draw a free body diagram. Everybody loves free body diagram. So let's go get our coordinate going first. Here's X, Y. And we've got A over here. We've got B over here. We've got our tension going up. Oh, and we're not worrying, no, never mind. I was going to say something, but it was going to be stupid and wrong. Whatever. So there's the tension force up, and then we have this first, the resultant, the FR term, right? The FR at 3/5 from L. So it'll be kind of over here a little bit, whatever. What's our FR? And then we have the weight of it acting 1/3 from A. So somewhere over here, I guess. And this will be W. So, this is L over 3. This is 3L over 5. All from A. Okay. And so now for the tension at T, let's do that one first, because it's the easiest. Well, I guess it's one you have to do first, because you don't know. Oh, yeah, and we have this, what we're solving for, this, what are we calling it? Calling it RA, reaction at A. Okay, so first off for T, for tension. Let's take the moments about point A. positive that way, equals 0, equals, so we're going to have minus weight times L over 3 minus FR times 3L over 5, and then plus T times L. Okay, so move everything over, right? We have TL equals W L over 3 plus FR 3L over 5. Divide by L, and you can just leave this in like the super simple form, just divide by L. So you have T equals W over 3 plus FR times 3 over 5. That's totally cool. You can leave that like that. That's okay. We all know what you're talking about. If you want to go and write all the stuff in there at the end, you totally can. But I'm not going to. It's okay. You know what's up. So lastly, now for the reaction A, super easy. Just take a sum of forces in the Y equals 0 equals, we have RA going up, so we're going to be solving for minus W minus FR plus T. And what says T? It's the W over 3 plus FR 3 over 5. So we have RA equals W plus FR minus T. And again, you can leave this in the super simple form where you just go substitute everything in. If you go substitute everything in and subtract the T, you get reaction at point A, RA equals to, should be 2 over 5 FR plus 2/3 W. Cool. And that's basically it. All right, there's part C all done for you. So this, in full disclosure, we don't use all that much of this stuff, especially the like integrating, integrating forces over like a surface like that for like pressure distribution and things like that. We don't do all that much in this class, but it's, it's a nice little statics review if you haven't taken a statics class in a little while. But anyway, there's that. I'll try and post this in all the Canvas pages along with the actual document here in a little bit. So there's that for you. If you have any questions, shoot me an email or leave a comment on the video. I'll try and get back to it as quick as I can. I'm usually pretty fast with this stuff. So anyway, have a good rest of the week, whatever you're doing. Have fun studying. Have fun doing homework. If you have anything else you need to ask me, just let me know. All right, thanks, guys.